And so you have ax equals b. That's the kind of thing we have. How do we make sure to solve it with one constraint? Okay, and what do people say? Here are some ideas. Ooh, I don't know. Very, very good. Columns, last, else, input. Okay, let's read the submissions one by one. I don't know. Very good. I guess I don't know, all lowercase is winning the battle of hearts and minds, so just start doing that. So the thing is, this is like what we want to solve. This is how you would write it down for a human, right? Like if you were a linear algebra teacher and you're like, please solve it, you would just like write that down and tell people to solve it. But how do you feed it into the computer? Ax plus b times 0. This might be close to the right kind of thing. Okay, this is a very nice one. Add a row in A with 1 in last column and a row in B with 0. This is perfectly right on. What you do is you encode x of 2 equals 0 as a linear equation, and then you stick that linear equation in A. That's the right idea. So let's see that. Let's see. Were there any other ideas? Yeah, this kind of thing also doesn't fit. But this is the right idea, is you add rows to A. So let's take a look at how this works. So I'm going to do it very specifically for the equation we had last class. This was for the 2 coins in a row, right? So V equals R plus MV. And the thing that is a little bit annoying is when you move this thing to the other side of the system, then you're going to get something like this. So you're going to get identity matrix minus M times V equals R, where what were the things? M is the probability transition matrix. I guess I was calling it P at some point, but let's go with M for matrix. The probability transition matrix. The probability transition matrix. And if you write down what these things are, the identity matrix is 1, 1, 1 with all zeros. And then minus, our matrix was 1 half, 1 half, 0, 1 half, 0, 1 half, 0, 0, 1, all times V. Equals, and the reward vector was 1, 1, 0, going plus 1 for the first 2 states and nothing in the last state. And if you do this kind of thing, you're going to see what it is 1 minus this thing is a half, 1 half, minus 1 half, 0. And then you get minus 1 half, 1, minus 1 half. And you get this annoying row of all zeros, V. So this is how you would write the equation in a computer, is you could convert it to this so that it's in the form A times X equals B. All right, and so now you try to put it in the computer. And once again, we're forgetting the issue. This is like how to enter in. And we want V of 2 to be equal to 0. That's what we're going to do in a second. There's also one other annoying problem in this matrix. Does anyone see the annoying problem? If you're working on the homework, you also might have run into the annoying problem about this matrix, I minus the transition. So this is I minus M, this matrix over here. And it has an annoying property. Yeah. It's not invertible. It has a row of all zeros over here. And that's because, we had the last entry was a terminal thing, and then when you do I, you have a 1 minus a 1, you have a row of all zeros. And in fact, any row that is a terminal state for the Markov chain, anything where you're stuck, will give a row of all zeros, okay? And that's a problem because if you put this in your computer and you say, please solve it, it will yell at you in a number of ways. And one of the things it might say is matrix not invertible, or like there's no solutions. So depending on how you put it in, you might have a problem. So one thing you can do already is you could just delete that row. This row is not saying anything. It says 0 times this vector v equals 0. Any vector v solves that. So already this is the same kind of system. You could just delete this thing over here. By the way, it's important that you have 0 reward over here. Otherwise, nothing will work. And that also makes sense too. Imagine if you got a reward every time you were in the terminal state, your total reward would be infinity, right? You just like sit there forever and pick up the reward. So this has to be 0 for this thing to make sense. Otherwise, the value function is just something that does not make sense. It will just be infinite. So that's one thing. We can delete this. And we sort of have a separate problem, which is how do we include this? And the way you can include that is to add it on as a row. So the way to include v of 2 equals 0 is you add on this condition that 0, 0, 1 times v equals, and in this case it's the number 0. And adding on this row, sometimes people call this an augmented matrix. And they draw a little line to show it's the augmented matrix. And they would write this as like a line, and then they would say like, I guess in this case it's E2, it's the vector E2, all times v equals r, and then the number is 0. And this is two equations sort of smashed together. It's the equation AV equals r and E2 dot v equals 0. And you can sort of do two equations at once if you just stack them on top of each other. And this is one possible way to fix the computer program that you have. In this particular case, you could have also like deleted this line and then had a nice square matrix as well. But in general, I think you normally just tack stuff on. So you don't want to get in the weeds with deleting stuff. It can be slightly annoying. Any questions or comments about the theory? I'm about to do it on the computer, but that's the theory part. Is we're gonna stack on the equation we want. We're gonna stack it on with the matrix, and then solve it that way. All right, let's see what this looks like. So I will open up the programming. Here is what we've been doing in class, which maybe we'll do one more in here, and then we'll start a new one because it's getting a little bit long. Okay. That was Tuesday. We didn't do any programming Tuesday, so I guess today is Thursday. Let's do some programming. Okay, and I guess we have the snakes and ladders. So let's do it for the snakes and ladders. We know in the snakes and ladders, for example, we figured out a few classes ago that in snakes and ladders, it takes 3.37 turns to get to the end on average. And we did it by doing an infinite sum. And today we're going to do it by doing some linear algebra. And we should also get 3.37. So I'm going to run the same thing as before. And then the point is that we have this matrix. We have transition matrix, which was the snakes and ladders matrix from a few classes ago. Okay. And you can absolutely solve this thing with the infinite sum. It's a totally valid way to do it. And we're going to do it the linear algebra way now. Okay. So what do I want to do? So the matrix that I have is going to be, let's call it I minus m. And it's the identity matrix, which in NumPy you do np.I, which is very, very funny that they did it I, like the thing in your eye. That's the left-hand side. And then I want to stack on this vector en. Let's call it en, which is, nope, not that, Google. I guess it's all zeros. And then I want to make en of the last entry, the ninth entry, equal to 1. That is that vector over there. And now I got to stack them on top of each other. Now I don't remember how to stack them on top of each other. So I'm going to look at my cheat sheet, which is my answers from earlier, to see how you stack them on top of each other. It's the command concatenate. Okay, so to concatenate them, we're going to do augmented matrix. I don't know what this C underscore is, but it's concatenate. Concatenate, and then you stack them together like this with a square bracket. And you do it on axis equals 0. Okay, it doesn't like me. Maybe I have to do them in the other order? Oh, okay. You have to put them with the... Still doesn't like me. Okay. Let me try it the other way. It works in my other code book this way. So maybe that's the problem. Okay, I'm gonna copy paste over here and see what does it not like. This is what I had before. I minus the transition matrix. Okay, this is a fantastic life lesson for you. So over here, I made an array of zeros with np.zeros, and now it's yelling at me. And it's like, I don't know what you're talking about. You cannot possibly stack an array of zeros, of 10 zeros, on top of a matrix. And so if you look at the sizes of these things, let's take a look. So en is a 10 comma vector, and I minus m is a 10 by 10. And I'm like, look, Mr. Computer, please put the 10 comma vector on top of the 10, 10. And it's like, no, man, that's totally batshit crazy. You can't do that. What you have to do instead is make a 1 by 10. You see this? np.0 is a 1 by 10. And then it'll work just fine. So let's do this. Okay, now we're not working for a different reason, which is that capitals. Let's transition matrix. I guess that means an underscore as well. And now it should work. So you can stack a 1 by 10 on top of a 10, but you cannot stop a 10 comma on top of a 10 by 10. And you can see this augmented matrix, it's an 11 by 10. So this is a good life lesson when you're working with these things. You got to get the shapes exactly right sometimes, and sometimes that means adding this 1 by 10, thinking of it as a row vector to stack on top. Okay, any questions or comments about how I made the computer get the augmented matrix and why it wasn't working before? All right, so then now the fun thing is, now we can solve it. There's a command, np.linalg.solve, and it basically solves ax equals b like this. So if you do this, and you do x equals np.linalg.solve a comma b, it will solve the equation ax equals b. Unfortunately, np.linalg.solve only works for square matrices. And our matrix is not a square matrix anymore, so you have to use a different command. Instead of the word solve, you have to use the word list squa. List squa. Does anyone know what list squa stands for? Not a common word you see in everyday language. Anyone want to take a guess? Here, you have a guess, or are you scratching your chin?
It looks like least squares.
It is least squares. That's exactly what it is. So np.linalg.solve will try to solve the system. np.linalg.least squares, which is this command, it will try to find the closest vector. So this is a good pro tip, which is that if you say like solve ax equals b, sometimes when there's no solution, the solve will break and like yell at you and be like, I couldn't find a solution, I'm so sad. Whereas if you say least squa ax equals b, what it does is it finds the x that minimizes ax minus b. It actually minimizes ax minus b squared. And so if that is not 0, it'll still return an answer. So this is like least squares is like a slightly more generalized version of solving where you're allowed to find like approximate solutions that are not the exact solution. That can be very nice sometimes. And in this particular case, it's nice because it lets you do non-square matrices. So if you do that, it will work just fine. Okay, so let's go back to this. And we wanted to do it with the augmented matrix. Okay, and this is to find the value function answer. And so we're going to be least squares. What do we have to put in as the vector? B. That's the vector of all these rewards that we had over here. So it's the vector that is all ones except for a 0 in the terminal state. If you put in all ones except a 0 in the terminal state, then it's counting how many times you visited all the non-terminal states. That's exactly what we want. So in our situation, let me copy and paste it over here. I think I called it roll again v at some point in the past. Maybe it's up here in the code. Yeah, here's the vector that we want. It's np.ones with a 0 at the end. I guess we called it v before, which is kind of confusing because everything's a v. So let's call it we call it roll again v. That's the vector of where do you roll again and where do you not roll again. And you roll again in all the states except the very last one. Okay, so if I run this with roll again, this should work. Roll again v. Let's see, will it work? Oh, yeah, sometimes you need this rcon equals none. That is telling the least squares to don't be too upset about things. And let me not get the 0 entry yet. Okay. Anyone have a prediction on what's going to happen when I hit run? Yeah.
I think it's not going to run because you need to augment v.
That's right. If I try to run this, it'll complain and say this vector is the wrong size. Let's run it and see. Okay, now it's complaining that I didn't put a bracket, but even if I had put the bracket, it should say incompatible dimensions. Linealge error, incompatible dimensions. And that's because, remember, this augmented matrix, it is not a square matrix anymore. It's a 10 by 10 matrix with one row added at the bottom. So it's an 11 by 10, and roll again v only had 10 things. So I have to tack on a thing. You could do concatenate again, or you could do a little hack and say roll again v with augmented, and then make it size 11. And actually, I want the last 2 entries to be 0 with augmented. So maybe a little hacky. Why don't we make this one? This is a nice thing you can do sometimes. Instead of putting in values, you put in variable names. So let's put in the v value at terminal state, and then let's make that 0 v value at terminal state. And then that way, somebody reading my code can understand what the hell's going on here. That's the very last entry. And the entry before that also has to be 2 as well, or 0 as well. So put in a -2, and that also has to be 0. That's just setting up the vector from before. Okay, so now it should run. Let's see if I'm right or if it complains. It still says incompatible dimensions, and probably oh yeah, because I gotta change the name. Okay, roll again v with augmented, and now it will work. Okay, what did it output? It outputted this matrix 4.37, 4.11, 4.11. It's a vector of size that we want, and it should tell you the number of steps until you reach the end. One thing that's bothering me is it's off by 1. This is 4.37. The answer we were looking for was 3.37, so I must have done something silly where I'm adding 1. I can't figure out what that is. Maybe someone else sees it. 0.9. Okay, well, we're pretty close. Why is it off by 1? Okay. Very interesting. Okay, well, let me in the interest of completeness, let me copy and paste the code I have over here. And this one really does work, or it did when I ran it earlier. Let's see, what's different about this one? This one I stacked a 0 on top. Well, okay, let's just leave it at that. I think what's going on is it also thinks that if you start in the final square, you still get a 1. So it's adding a +1 everywhere for a reason I cannot understand, and I will leave it as an exercise. Maybe find the bug. There's some kind of extra +1 somewhere, which if you set this to like, let's set this to 17. It should add 17 to everything. Let's see. Did it add 17 to everything? It did not. So something's a little funny. All right, let me stop there. That's the linear algebra way to do it. And if you get it just right, it will work. I promise. Now it's really bothering me. But okay, any questions or comments about that other than why isn't it working? The main point of today's class is don't do the linear algebra way. There's a better way to do it that we're going to learn. So you can do this stuff with linear algebra, and you got to get it just right. But we're going to learn a different way. So that's the sort of the end of the linear algebra way. And we're going to learn a new way called value iteration. And value iteration is in a lot of ways better. I will try to highlight a lot of the ways. One of the ways is like, it's easier to intuit what is going on. It's like easier to find bugs. So I'm sure I have some dumb bug over here with where I put these things in and how you have to augment the matrix and so on and so on. And that's probably what's going on. But before I move on to that, any other questions about the linear algebra? I don't super recommend the linear algebra, and you'll see why it's bad when we do value iteration. Okay, to get this value iteration ball rolling, I came up with a fun problem for you guys to try, which is this problem you might have had when you were in elementary school. So you have a calculator, and you want to find a solution to x equals cosine of x. How do you solve x equals cosine of x with your calculator? And you sit there, you're bored in class, you're pressing the buttons. You might have stumbled upon this solution anyway. I'll draw a little graph. So here's the cosine. What does cosine start at? At 1, and it goes down. So this is y equals cosine of x. And then this is y equals x. How do you figure out this point of intersection using your regular calculator? Okay, I'll let you guys brainstorm for a bit. Maybe you'll have thought of this. And also, while you're doing that, maybe I'll try to debug my code, maybe to find what the silly bug was. But I'll give you 2 minutes to think about that. Solve x equals cosine of x using an ordinary calculator. give me 2 seconds here. I think I have discovered. Okay, before I tell you guys how to solve for x equals cosine of x, I have found the bug in this thing, and I think it's a good learning lesson. So I'm going to show you what the bug was. Do you remember, I did a really dumb hack of like, oh, instead of writing it with a concatenate, let me just like cram it in there. So really what I should have done is I should have had roll again v, which is this vector of all ones and then a 0. So this should be 0. Okay, very good. And then I took the value at the terminal state, which is just 0. You got to make it an array, and then you concatenate them on top of each other. And if you look, that is exactly what I did. So far I have not changed the code. I have just rewritten it in a nicer way. And if you run it, you get the same bug as before. Okay, so 4.37. But now, if you are looking at it, you should be able to see the bug more easily. What did I do wrong? And you can compare this line 14 with this line 6, and you should be able to see what the bug is. I think this is a good debugging lesson. And this is the kind of mistake you will make hundreds of times in your programming assignments. Yeah.
Is it the axis?
It's not the axis. So the axis is saying put them on top of each other, but don't put them next to each other. That part is okay. And yeah, let me compare to the math, right? So this is like a lot of the shebang in this course is converting math into programming. So on one side, I said, take the matrix and the vector and put them next to each other. And that was this line over here. And actually, look, I did it. I said, take the equation and then put it on top of the matrix. So I actually did it in the opposite order of what I said over here. And so I actually have this. I have E2 and then A on top, and then I'm hitting V. But then over here, I did it the other way. So I have the roll again vector, all that vectors of ones, and then I put the final value over there. So I kind of flipped it. When I concatenated them, I did them in the opposite orders. So I did this R0. And so my left-hand side, I stacked them on top of each other in the opposite way. I'm going to get like some other equation that is not what I think it is at all. So the bug should be just flipping these. The v value at the terminal state. I guess let me be consistent with what I wrote in the first place in the math, was to stick it on at the bottom. And now it should work. Let's see, does it work now? I'll be really embarrassed if it doesn't work now. 3.37 times 10 to the 0. Okay, great. So this vector is telling you how many rolls does it take to get to the end, but as a function of where you start. And if you start at square 0, it takes 3.37 rolls. If you start in the final square, I guess it thinks it takes 6 times 10 to the minus 16, also known as very close to 0 rolls to get to the end. So that's very good. Okay, so we fixed it. So that was the bug, is I had the order switched. This is a very common type of bug that you'll see, and you should sort of get practice with trying to stare at code and figure out these kinds of things and how do you debug it. That's a large part of the programming assignments. Okay, questions or comments before I move on to cosine of x equals x? All right, let's see cosine of x equals x. What did people say? And this one is in this window over here. Oh, okay, great. Look at all these ideas. Okay, keep, random, point, output, repeated. I like repeated. Okay, let's see. Oh, I don't want to reveal I want to reveal all your answers. Okay. Cos inverse of x. Cos inverse will not help you because when you do x equals cosine of x, if you apply cos inverse to both sides of the equation, then on the left-hand side you have cos inverse of x, and on the right-hand side you have x. So, turning this into this, you haven't actually made any progress. You still got to solve what x is. Okay. This is a nice one. Take cosine of 1 and then take the cosine of that answer and the cosine of that answer and so on. This is exactly the right thing. This is the same thing as this one. Repeated application. Iterate. Very nice. Yeah, so these iterations, when you have x equals something, you can solve it by just repeating it over and over again. And to show you, I brought my calculator app. And here it is. Here, I was testing it earlier to make sure that it works. You can start with any value you want. Let's start with, I don't know, 3.14. That's a nice approximation of pi. And we'll hit cosine, close to -1. Cosine again, 0.54. Cosine again, 0.85. Cosine again, 0.65. Again, 0.79. 0.7, 0.76, 7.2, 7.5, 7.3, 7.4, 7.3, 7.4, 7.3, 7.4, 7.3, 7.4. Oh, no, 7.38. And if we just keep hitting this, we just get it gets closer and closer to not changing. So if I just hit this a bunch more times, then we're at 0.739. And for sure, you have done this in your life. If you're very bored in math class, hitting the cosine button over and over again becomes very tempting. And this is a number where it's a number x, and if I apply and try to figure out what is cosine of x is very close to x. So we've found the solution to x equals cosine of x almost by accident by just spamming the cosine button on our calculator, okay? And this is a very useful thing. This is called a fixed point equation, as some people figured out. So the idea is fixed point equations x equals, it could be any function of x, are easy to solve by repeatedly applying f. Repeatedly applying f. And why don't we make a little theorem out of this? So let's make a theorem. Here's a theorem. We're going to say, make a sequence, let x k plus 1 equal f of xk. So x0, x1, dot, dot, dot is a sequence. So that's the sequence of the x values you just saw. So I could have written them all down as I was going in my calculator app, which I cannot find. Okay, here it is. So, right? That was the sequence of values. I started at 3.14, and then I just applied the cosine function over and over again. That makes a sequence of values. And let's suppose the limit exists. X star is the limit as k goes to infinity of xk. So the limit of the sequence. Then x star equals f of x star. So whatever this sequence is getting closer and closer to must be a solution to the equation that we wanted. This is called a fixed point equation because applying f to x star doesn't move it. So x star is fixed under the action of f. And I'm missing one technical, I need one technical condition. And we will discover what the technical condition is as we go. Maybe you can guess what the technical condition has to be. But here is the proof of the theorem. And the proof of the theorem just starts with, you got xk plus 1 equal f of xk. Take the limit of the left-hand side and the right-hand side. Take the limit of both sides. So on the left-hand side, it's the limit as k goes to infinity of xk plus 1. On the right-hand side, it's the limit as k goes to infinity of f of xk. This thing, having a k plus 1, if k is getting bigger and bigger to infinity, that's still x star. So the left-hand side equals x star. The right-hand side, what is the right-hand side? Well, it's the limit as x goes to infinity of f of xk. It would be so nice if we could say that is f of x star. But that's not always true. So some functions f that's true, some functions f that's not true. This is where we need the technical condition on f. Does anyone know what kind of technical condition would make sure this is okay? Yeah.
The difference would be negative in summing or whatever what it is.
Yeah, I think you have the right idea, is that we need to make sure f is like a nice function, like well-behaved enough that this is okay. You're making it nicer than it has to be. Yeah.
F is continuous.
It just has to be continuous. So continuous functions have the property f must be continuous. And continuous functions have this property that you can pull limits in and out. So the right-hand side is the limit as x goes to infinity of f of xk. And for continuous functions, that's the same as f of the limit as x goes to infinity of xk. This is since f is continuous. This is like one potential definition of a continuous function, is that it satisfies this. And that's equal to f of x star. So as long as the limit exists and the function is continuous, then any limit will be a fixed point. You might also be suspicious in the way I've worded this. I've said, suppose the limit exists, then it does what we want. You might also wonder, in what situations does the limit exist? Question. Does the limit always exist? And the answer is not always, but one sufficient condition, not always. One sufficient condition is for f to be a contraction. Yes, if f is a contraction. And a contraction means it smooshes things. F of x minus y has to be sort of less than or equal to x minus y. So this is sort of technical. If you are not into the technical side of things, you can just cross your fingers and hope that f will work. And I will tell you, in our equation, we had the equation we wanted was v equals r plus m times v. I'll say, if you put in a gamma, it is for sure a contraction, is a proper contraction when gamma is less than 1. So as soon as gamma is even a little bit less than 1, everything will work perfectly fine, and you'll have nice guarantees that everything will work. And when gamma equals 1, it will sometimes work. Gamma equals 1 usually works. I'll say usually, and not worry too much. But the punchline is, if you want to solve this equation, and you have v on the left-hand side, and you have some function of v, just apply it over and over again, and we will hope that it converges. And this will work. Okay. Questions or comments? This is sort of all the theory. We're going to apply it now. Yeah?
Don't you need like a gamma in the inequality?
Yes. Okay, this is, so I put it like this. There should be a lambda with lambda strictly less than 1. There you go. So there has to be some shrinking constant, and the role gamma plays the same role as the lambda. That's a good one. Yeah. Yeah. So if you want to look up a buzzword, there's a theorem called the Banach fixed point theorem. Banach being some German guy. Banach fixed point theorem. And there's all sorts of different ones that are more complicated or less complicated. If you want to analyze this thing for vectors and matrices, you technically got to worry about the eigenvalues of this matrix, but it will work out. Other questions or comments about the theory? Okay, so let's see it in action. And what I hope to convince you in the rest of the class today is that this fixed point thing, which if you do it fixed point equation specifically for this, it's called value iteration. I'm going to try to convince you it's better than the linear algebra way. I'm going to try to convince you that in almost all the ways you can think of, it's better. Let's start with the example we had before. And then we're going to do a more fun example, but let's start with the one we were doing already. Okay. So instead of doing all this stuff with like augmenting the matrix and worrying about least squares versus like solve, all you got to do is do a loop, and you're going to have some number of iterations. That's the number of times you're going to press the button on your calculator. And I'm going to start with the transition matrix. What do I have? Yeah, I got the roll again v. Okay, great. So the value function, you can start it out as anything you want. Let's make it all zeros, say. This is the initial guess. Initial. Okay, and then I'm going to start with v is going to be whatever the initial value is. And I'm going to loop through these number of iterations. So for iter in range num iters. And I'm just going to apply the equation. So I'm going to do v equals, not what Google is suggesting, but I'm going to do the reward v. What was it called? It had a name. Was it reward vec? What did we add on? Roll again V. Okay, what a beautiful name. Roll again V plus transition matrix times V. And we can print this out after any number of things. So there it is. You don't have to worry about augmenting or anything. You just apply the equation again and again and again. We want to find a solution that satisfies this. Like in math land, we want V equals this. In computer land, we say V equals that, and then it will set it equal to the thing. We are doing the rule that exactly over here, that the next guess is the previous guess. So this is how we implemented this line, and the iteration variable is what I called k before. Okay. And I told it to print it out after everything. So a very short 4-line program, very easy to read. And look at that. Look at how quickly 3.37 is the answer we wanted. I guess if I scroll up, you see it started out as 1, 1, 1, 1, 1, and then it went up to 2, and then 2.6, and it's kind of going up to the right answer, which is the number of rolls you need. There we go. Questions or comments about this one? It's a lot easier. You don't have to worry about the augmented matrix and all that. One potential downside is you might worry that maybe this num iters thing is annoying, but it turns out doing a matrix inverse is also annoying. So this way is a little nicer. Questions or comments? I will say this might remind you of something we did earlier in class, which is earlier we had something that was also, it was an infinite sum. There's no infinite sum here, right? I'm just applying this thing over and over again. There's no, as written, there's no infinite sum. You don't need to worry about writing things up. But I claim there's an interesting thing, which is that here is an interesting factoid. Value iteration started from an initial guess of V0 equals 0 is the same as the infinite sum. From, I guess, a few classes ago, let's say last week. So this is the claim. The thing we're actually doing, we've discovered a nice way to like explain it. Like we have this equation that we're trying to solve, the Bellman equation, and we're solving it by repeatedly applying it. And it turns out we get exactly the same interpretation we had as last class with the infinite sum. And here's the proof. The proof is just what you just write down what everything is. So the claim is that Vk, which is k iterations of the value iteration, it equals the sum from, let's call it I going from 0 to k of p to the I times r. Yeah, that's what it is. Times r. Okay, and the proof is I'm gonna do them. So v0 equals 0. That's very good. What is v1? V1, the rule is you do r plus p times v0. And v0 is the 0 vector, so you just get r. So after one iteration, you have r, the reward vector. You might have noticed that in what we just did. So, I've lost the internet. Okay. Here it is. Okay. So after one iteration, it's the vector, the reward vector, 1, 1, 1, 1, 1, 0. What is it after 2 iterations? Let's find out. So after 2 iterations, got v2. Well, the rule is r plus p times v1. And what is p times v1? It's p times the vector r. So you take this in, plug it in, p times r. So you have the matrix I plus p times r if you want, adding up the thing. And now when you do v3, then you do r plus p times r. Right? Every single vector from v2 gets a p applied to it, and then you add on an r at the beginning. So this will be r plus I plus p times p r. And then you see sort of where this thing is coming from. It's r plus p times r plus p squared times r. So every time you go one level in the iteration, you sort of apply p to everything, that shifts it all over, and then you tack on that first term. So maybe I will skip the details. If you want, you can do a proof by induction. But vk, it's always r plus p times vk minus 1. And this shifts everything over by 1. So you do r times p times I plus p dot 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 plus p to the k minus 1 times r. So you're sort of taking the previous vector, which is the sum of the k minus 1 things, you shift it over by 1 with p, and then you add on r. And now you have the full thing. So it's r plus p times r plus p squared times r plus dot dot dot, all the way up to p to the k times r, which is what we wanted. So doing value iteration is kind of a quick and easy way of doing the infinite sums from a few classes ago, and it kind of has a more nice way of thinking about it as a way of solving the equation. Okay. We're going to do some more examples with value iteration. I think it is one of the most important ideas in the class. Later on, we're going to move away from situations where you know all the rules. Like in all these games, we started with the matrix P. We're going to look at situations where you don't know the matrix P and you're sort of learning it by doing. But this value iteration idea will continue. So we're always going to be doing stuff like this. A lot of the things in the course are sort of variations on this value iteration idea. Any other questions or comments? Yeah.
So there has to be some sort of condition on P then in order for it to converge.
Yes, so here's the thing. P is, we know it is the transition matrix for a Markov chain. So like in particular, all the entries are non-zero, they're positive, and they add up to 1 in every row. So that is called a stochastic matrix. So let me give you a little thing if you're worried about this kind of thing. There's a theorem called the Perron-Frobenius theorem. So this is, again, very technical, and it kind of explains why these things work. And the Perron-Frobenius theorem says, for a stochastic matrix, let's call it M. And a stochastic matrix means all entries between 0 and 1, and rows sum to 1. So any kind of matrix you make that has this property, that all the entries are between 0 and 1 and the rows sum to 1, it will have one, maybe I shouldn't say 1, okay. All the eigenvalues are also in 0 and 1. Let's leave it like that. It says more specific things, but this is one of them. All the eigenvalues are between 0 and 1. And in particular, sometimes it says, it approximately says that other than terminal states, all eigenvalues. Maybe I should say it. I'll say other than terminal states, I'm going to put / steady states. All eigenvalues are in 0, 1, with 1 excluded. So when you do an infinite sum like this, it converges as fast as the eigenvalues of the matrix P. And this kind of theorem says, don't worry, it's going to be fine. The eigenvalues of the matrix P are well behaved. You can potentially have problems. And indeed, if the reward vector R, if it had a non-zero entry in the terminal state, then this thing would explode to infinity, right? And that's because you would be picking up a reward every time you are at the terminal state. And so how much time are you spending in the terminal state? That goes to infinity in this situation. But other than that one, all the convergence will be nice. So as long as the reward is 0 in the terminal states, things will be okay. So this is kind of like a theoretical reason why the value iteration will converge. The textbook also has a few different reasons why it will converge as well, so you can also read that. I'm not going to ask you any theory questions about this stuff. You'll just run it, and either it'll work or not. Yeah, fantastic question. Anyone else? Okay, let's do another example. And the example I want to do is a really famous problem in sort of like probability or in this area. Let's see if I can get it open in Mathematize. Yeah, here it is. And the problem I'm going to do is called the Drunkard's Walk. And it's a fun problem that goes like this. So a drunkard, he leaves a bar and the bar is in the middle of Main Street. And their house is X steps to the left of the bar, but then a deadly cliff is Y steps to the right of the bar. And instead of walking home, they kind of walk around randomly. So sometimes they take a step left, sometimes they take a step right, and you can have a probability P and 1 minus P of doing these two different things. Classically, it's 50-50, so like they're walking around totally at random. And what we're going to do is we're going to turn this thing into a Markov chain, and there's a lot of different fun questions you can ask about the drunkard. I want you to think of one question that you can ask about this that you think is an interesting question, and then think of what is the Markov chain and how would you answer the question that you are thinking of. So I'll give you a few minutes to do that. In your answer, you only have to put in the question. So like something you're curious about this drunkard, like, what's the chance he does this or that? Or like how long does it take? Think of any question you want. If you can come up with the matrix, that's a good way to check. The matrix also has a really nice form. It looks a certain way. So I'll let you guys think about this for a few minutes, and then we'll reconvene, say, in 2 minutes, say. So think about this drunkard, and then we're gonna solve it. Okay, 20 seconds left for you to give me whatever questions you would like to know about the drunkard, and then we will simulate them on our computer and try to answer these questions. Okay, let's take a look. I guess this is still counting down. Okay. What questions do people want to answer? Ooh, okay. Are there any other obstacles? No, it's just him walking. This is the classical question that most people ask. What is the probability he's home after T steps? How many steps does he take until he falls off? Like what time will he get home? His variance. How likely is he to arrive at home? And so on and so on. Are they alone? Well, he's at the bar and he's leaving, so I don't know. What is the chance of falling off the cliff? These are great questions. So let's draw a little picture of the situation. So we have this guy. He's at the bar, which is at this location X. We can call it like X initial or something too. And then there's a house over here. This is the house. And that's some number of steps to one side. And then all the way over here, there's some number of steps. And this is the deadly cliff. I don't know, how do you draw a deadly cliff? Like this. I don't know, cliff. Okay. And depending on where he starts, like how far away this is, he's going to be more or less likely to fall off the cliff or fall at home. We can figure this out as a Markov chain because you make the states. The states are the locations. So, there's location 0, there's location 1. So 0 could be the house. And the cliff could be all the way over here. Let's make n the cliff. Note that the number of states is n plus 1, and x in it will be the bar. And you got all the places in between. So what does the Markov chain matrix look like? It's going to be some big n plus 1 by n plus 1 matrix. N plus 1 by n plus 1 matrix. And I'll tell you some of the ones that I know for sure. There's a 1 in the corners. Why is there a 1 in the corners? Well, if you are on the final states are terminal states. So the cliff, if you're in the cliff, you stay at the cliff forever. If you're at home, you stay at home forever. And it's the in-between states, 1 to n minus 1. Those are the states where something can happen. So you got to fill in what this looks like. Any questions about the setup so far? Okay, I'll let you guys think for a second. How do you fill in the matrix? And remember, let's do the 50-50 case. So let's say he moves left with probability 50% to go left and 50% to go right. What would that look like in the matrix? So I'll give you a second to do it, and I'm going to start a new notebook for us. We're going to do it in the notebook and get some nice pictures of this thing. Okay, I'm going to do it in the computer, and then we can compare the computer's answer to the paper answer. So I have a brand new notebook, and I made n equal 10, so there's 11 states. N plus 1 states going from 0 to 10. And we're going to say x in it is 3, so the bar is 3 steps over. And we're going to say the house is at 0, and the cliff is at 10. So actually, why don't we do it the other way around? Let's make 0 the cliff. 0 is the cliff, and n is the house. Okay, great. So how are we going to make this matrix M? Well, it's going to be a matrix that is size n plus 1 by n plus 1. And I told you some of the entries already. M00 is 1, and MNN is 1. By the way, yeah, so those are sort of terminal states, and terminal states always have this property. You stay there forever. In a lot of situations, you sort of have to hand code in the terminal states. But now we're going to try to code in these other states, and we're going to say it's 50-50 to step left or right. Left or right at other states. And you could do this with a for loop. So you could do for x in range n, and I guess I want 1 to n. And then I'll say m of x. I'll say that, yeah, let's do it the old-fashioned way. From square is x, and the from square equals x, and the to square equals x minus 1, or let's do x plus 1, and then m of from square 2 squared equals 0.5. That's kind of similar to our stakes and ladders situation. All right, very good. And we got to do the opposite as well. So let's flip it one more time. The from square is x, and the to square is x minus 1, and then from square 2 square is also 0.5. So that should make our matrix. If we did it right, we'll have a nice picture of the matrix. Let's see. And here is what the matrix looks like. It's got 1s in the corner, and then in the non-corners, it has this funny little like zeros in most of it, and then it has 0.5s in what is called the super diagonal and the subdiagonal. So just below the diagonal, we have a bunch of 0.5s. So that's what it looks like. Okay, so I guess I can fill it in now. It's got a bunch of 1/2s. 1/2, 1/2, 1/2, 1/2. All the way in the subdiagonal here. Okay, and then it has zeros right in the middle. 0 to 0. Okay, that's what the matrix looks like. You could also put p in 1 minus p if you wanted him to have different probabilities, but let's just go with the 50-50 spot. Okay, yeah.
So tell us something. So in the code,
Yeah.
this is an n by n matrix, right?
It's an n. Well, it's an.
Never mind. Okay, sorry.
Yes, this is really important. Is to remember that Python always starts at 0, and so I made sure to make it n plus 1 by n plus 1. I believe in your assignment there's a bunch that are like this as well, where.
Yeah, there's confusion why when you reach n, it would have ignored the last row and then still put it. Just
That's right. Yeah. Okay. This is another thing. Is range 1 to n. You really should write it like this: range 1 to n minus 1 plus 1. because in Python, it always ignores the last number. So I often write it like this. So the last number it's actually going to do is n minus 1. And the plus 1 is just there because it ignores the last number. So yeah, that's just the way Python works. So you have to get used to it. Yeah, great, fantastic comment. All right. Before we go any further, I will say, as you get good with Python, you will learn tricks. And one trick in particular that is good to be on the lookout for is try to eliminate as many for loops as you can. So for loops, if you can get rid of them, it makes your code way faster and way easier to read. And a good hint that you can get rid of a for loop is if the for loop doesn't depend on the results of the other for loops. So here I'm doing x and x plus 1. There's no reason I can't do all of these at the same time. And so let me show you like the same code, but a little bit nicer. You can do all the x values from 1 to n minus 1. You can do them at once by just making them an array. So if I do np.a range 1 to n, that will give me, and again I should do n minus 1 plus 1. This is all values between 1 and n minus 1. And then you can just set it like this. You can do all the values, x, hopefully, yeah, there we go. X values this plus 1, you can set them all to 0.5 at the same time. So you can feed an array into an array, and it will get all of those for you. So this line of code is doing everything that this for loop was doing in these 4 lines, and it's doing it faster and easier to read. So I made the variable names a little bit long, but other than that, so that's doing half of it. So you should see, okay, I gotta restart by m. Let's make m zeros again, so you can see what's going on. Okay, let's copy this part. Okay, so that's half of the thing. So that's all the plus 1 steps. And if you want to do the minus 1 steps, you can do this as well. So sort of the bigger your programs get, the more you want to avoid for loops and silly things like this. But that does the exact same thing as before, and that's just a faster way to do all the things at once. There you go. That's the matrix M. Okay, now we're going to start to answer some of these questions. The 2 questions that I think are the ones we want to answer are question 1, which place does he end up? And question 2, how long does it take? And anytime you come up with a question like this, what you want to do is come up with a bunch of rewards, like values you put on the Markov chain, so that the expected number of values, when you find that value function using the Bellman equation, will answer these questions. And so both of these, question 1 and question 2, there's different ways you can cook up the rewards to make them do what you want. The how long does it take is actually very similar to what we just did, but which place does he end up? This one is a little bit weird. What I'm going to do is I'm going to try to make it so that, here's my attempt. I'm going to try to make it the house. I have these flipped in the code. Let me flip them over here as well. Okay, so let me. Over here will be the house, and over here will be the cliff. I'm gonna try to make it like this. I'm gonna try to make the cliff 0 life points, and if you make it home, then you get one life point. And so if I can give you a reward of 1 life point over there and a reward of 0 life points over here, and I just say, on average, how many life points do you get in total, that will be the probability of you making it there. So by assigning these life points, I can try to calculate the probability you end up somewhere by just calculating the expected number of life points starting from x. So the expected number n life points, that will be equal to the probability that you ended at the house. So this is the same kind of trick as before. So those are the rewards I want to cook up. It is slightly annoying to do this because I told you that at a terminal state, you can't have rewards, right? At a terminal state, you cannot give somebody 1 life point, because then what's going to happen is he's going to get to the house, and he's going to stay at the house forever, and he's going to pick up like infinitely many life points. I don't want to give him infinitely many life points. I want to give him 1 life point. Good job, you made it home. 1 point, not infinitely many points. And if I did that, if I gave him infinitely many points, then this would be infinity anyway. So nothing would work. So this is like the question, and this is going to be a really common issue, is how do I cook things up so that if you make it to the house, you get 1 point, and if you make it to the cliff, you get 0 points. 0 is okay, but how do I deal with the 1? Okay, and here are some options. So I'm going to give you 3 options. Here is option 1. I make another state in the game called done. So here's a state called done. What does done look like? I guess it's a little square. Okay, and then I put 0 to n over here, and then I have a transition. I make it so n is not a terminal state like it was before. N takes you to done, and 0 also takes you to done, and then done is a terminal state. So if you do that, then I can attach a reward of +1 to this transition from n to 0. So that's one possibility. So we're kind of doing this 50-50 walk everywhere. And then we have this like super special done state. And we're just like keeping track. You get a reward of +1, you go to done, and then everything's fine. And you have to make the matrix 1 bigger. Instead of being n+1 by n+1, now it's n+2 by n+2, because you have this extra done state. That's one way to do it. Here's another option, option 2. What you could do is the states that lead into the reward state, you give the reward there. So since in this particular situation, the only way to get to the final state over here is from here. Why don't I give a reward of +1 when you step from n-1 to n? So put a reward here. That's another way to do it. So here's n-1 to n, and I say if you move from n-1 to n, then you get a reward of +1. If you do this, you end up with silly looking things like the reward vector. That's what we called R before. That reward vector will look like this. It'll look like 0, 0, 0, and then it'll have a 1/2 and then a 0. Why does it have a 1/2? Because when you are in state n-1, you have a 1/2 chance of getting a reward of +1. So the reward vector R from the Bellman equation was the average thing. So you end up with silly things like this that are annoying. So those are options 1 and options 2. And these are both fine conceptually. So like if you want to think of it this way, you totally can. But the way we're going to do everything in this course on the computers is we're just going to do option 3, which is to just hard code in v of 0 equals 0 and v of n equals 1. So you can say, I'm going to do the Bellman equation, and anytime I'm at a terminal state, you should not think of the terminal state as being specified by the Bellman equation. You should just think of putting it in by fiat. And that is kind of how we started today's class as well, right? By augmenting the matrix with this thing. And I'm going to show you that as long as you make sure to always do this, so you have the terminal states and you always specify their value, then the Bellman equation will solve for all the other states. So think of Bellman equation as applying to all other states. And so we sort of like always keep these things as working. I do think this option 3 picture, which is what we're going to do in practice, is extremely similar to like a lazy man's option 1. So like we're really thinking of what is the value of state n? Well, the value is +1 because you're definitely going to get a reward of +1 and move to the done state. It's just I never write down what the done state is. And when I solve for the value function v, I'm just keeping track of this reward, right? Of the +1 that you're going to get 100% of the time. Why don't I just like write that down? That v of n equals 1 and leave it at that. So that's what we're going to do. And you're going to see how this works in code. And again, this is what I come down to as when I think of terminal rewards versus ongoing rewards, right? That I think I mentioned last class. Terminal rewards versus ongoing rewards. And ongoing rewards I think of as things that you really get on the way. And terminal rewards are like these ones, where I just hard code in their values. And if you want to make them all equivalent, you can just say like, oh, there's a picture like this where there's a special done state. But I'm not going to do it that way. So a terminal reward is really just specify the value of v at the terminal states. Okay, and in this case, I want to specify them like this. All right, I will run this quickly on the computer and show you a nice graph, and then we'll call it a day. But any questions or comments before that happens? All right, let me show you the thing. I won't do the full coding. Okay, I guess I want the reward vector to be all zeros. Give me one second here to change this to the example that I want. Okay, that's M. That's the matrix M. R is 0, and V of n equals 1. Okay. Oh, it says the computer says I have too many Colab sessions open. Please stop hogging all our computing. Okay, let's try again. Okay. So here's the matrix M that we had before, and here is what you get when you run value iteration to try to figure out the probability of falling off the cliff or not by setting up the rewards. Like I said, here is iterations 0, 1, 2, 3, 4. So at iteration 0, we think there's a 0% chance you will survive anywhere. And then as the iterations increase, we're getting closer and closer to your real probability. So 0, 1, 2, 3, 4. And then over time, it's converging, just like when you press cosine on your calculator over and over again, it converges to a super special function that tells you what is your chance of surviving from any given location. And I will let you guess what is the formula for this very fancy function, and we'll take it up next class. And this tells you what is your chance of surviving when the bar is x units away from the cliff. Okay, we'll do that next class. Have a good weekend. Don't forget about your assignment due, and I'll be around for questions if you have any.